Greetings everyone, this is Professor Roman. Let's continue the field theory lectures. We're ready now for Chapter 7, Solvability by Radicals. This is perhaps the pinnacle of elementary field theory, or at the very least the most famous result in field theory, namely that there is no general algebraic formula for polynomial equations of degree 5 or greater. In this chapter, as in the previous chapter, I'm going to assume that all fields have characteristic 0. And so all extensions are separable and all normal extensions are Galois. This is not necessary. We can do the theory without this assumption, but it does become more complex and doesn't really shed any additional insight into what's going on. I want to start this discussion with a quick review of radical extensions, because it's been a little while since we've discussed them. Here's the definition: a tower of fields where the kth step is either trivial or is an n-kth root extension, so the type of the root can vary from step to step, is called a radical tower. And the full extension FR is called a radical extension. Another way to express a radical tower is in this form. At each step we adjoin an element alpha sub k of type nk. It's type nk witness for the step. These are for the non-trivial steps. And I'm going to refer to these types n1 through nm as the step types for the extension FR. Here is a repeat of an earlier theorem from chapter 4. Properties of radical extensions. First we have lifting. Root extensions are closed under lifting. That is, if FE is a root extension of type n and FK is any extension, then we lift to get the extension KEK that is also a root extension of type n. It could certainly be a root extension of a smaller type, but it is of type n as well. If we have a radical tower and a field extension, then we can compose k with each term in the tower, and we get this tower. This is also a radical tower with the same step types as the original. And the class of radical extensions is closed under lifting. We have concatenation. If FR and RS are radical, then so is the full extension FS. Composite. If FR and FS are radical extensions, so is FRS. Normal closure. If FR is a radical extension, so is F normal closure of R over F. This is going to turn out to be critically important when we get to the main result. Definition. A field extension FS is solvable by radicals if it's contained in a radical extension FR, meaning that S lies between F and R. A polynomial p of x over f, or the corresponding equation p of x equals 0, is solvable by radicals in an algebraic closure f bar if its splitting field extension in f bar is solvable by radicals. Finally, a theorem. A finite extension fe is expressible by formula if and only if it is solvable by radicals. You might want, if this doesn't sound familiar, you might want to go back and look at an earlier video or go back in the book and take a look. A polynomial p of x is solvable by radicals if and only if the roots of p of x in an algebraic closure are expressible by formula. I don't think part 3 here I discussed earlier in the course, so let p of x be an irreducible polynomial over f with a root alpha in f bar. Then alpha is expressible by formula over f if and only if all of the roots of p of x in f bar are expressible by formula. So this is an all or nothing situation. All the roots are expressible by formula or none of them are. Hence, p of x is solvable by radicals if and only if any root of p of x is expressible by formula. As to the proof for part 3, if fs is a splitting field extension for p of x, then it is a normal, S is a normal closure of f with alpha adjoined over f. Now, if alpha is expressible by formula, then this extension is a radical extension. We had a theorem to the effect that if the generators are expressible by formula, the whole extension is. So this is a radical extension, and so theorem 7.1 tells us that fs is also radical because it's the normal closure extension. And since it's finite and radical, it's expressible by formula, which means that every root of p of x is expressible by formula. So if one root is, all the roots are. This is going to be significant to us because you might say, well, maybe there's an algebraic formula for one root of a fifth degree polynomial. Well, if there is, then there's going to be an algebraic formula for all the roots. Okay, let's talk now about tower properties and the Galois maps. When each step in a tower of either fields or groups, we'll be discussing both, belongs to a specific class of extensions, I'll call it script C, and it's reasonable to refer to the tower itself as having class C. This is just terminology. So here it is more officially. Let C be a class of field or group extensions. If each step in a tower is of class C, we will say that the tower has class C. This notation I'm using here is a way to condense the text rather than have to say this twice, once for field extensions, once for group extensions. I'm using this technique. It saves a lot of writing. If an extension AB has a tower decomposition of class C, then I'm going to say that the extension is a tower C extension, or simply is tower C. This is not standard notation or terminology, but there really is none, and I think this is worth doing because I think it helps with the clarity of the discussion, but that's a matter of opinion. You may not find it so. Finally, if G is a group and this extension, so it's the trivial subgroup to G, is tower C, we'll just say that G is tower C. So to say that G is tower C means this particular extension has a tower C decomposition. It sounds a little funny to say tower C, but C might be abelian, so it would be tower abelian, or cyclic, tower cyclic. So a normal tower of groups or fields is a tower in which each step is normal. An abelian tower of fields is a tower in which each step is abelian. Now remember, to say that a field extension is abelian is to say that its Galois group is abelian. The extension has to be Galois, and its Galois group is abelian. A cyclic tower is a tower in which each step is cyclic. There is an exception to this terminology, and I'm not about to change something that's already set in stone. A root tower is called a radical tower. When each step in a tower is a root extension, that's a radical tower. Now we can say that because the class of a tower depends independently on the class of the individual steps, we have automatically the concatenation property. So if C is a class of fields or group extensions, and if we have a two-tower ABC, then AB and BC, the individual steps being tower C, implies the whole extension is tower C. Because you just tack one C tower after the other. They connect up at B. Okay, now we want to apply the Galois maps to towers. So let FE be a finite Galois extension. So all the elements of the Galois correspondence are closed, and a theorem back in chapter 5 tells us that the Galois maps, haven't seen this in a while, are inverse order anti-isomorphisms between the families F of intermediate fields and the families G of subgroups of the Galois group. This should be singular. So the Galois maps then can be applied to every term in a tower, so they induce inverse degree-preserving bijections between the family of tower decompositions of FE and the tower decompositions of the Galois group. So specifically, if we have a tower decomposition of FE, and I'm using script T, so one here to denote the tower. Haven't done this before, but haven't had a reason to. This is sent by the Galois group map, G of T1, to this tower. I just apply the Galois group map to each term in this tower. And a tower decomposition of the Galois group is sent to this tower by the fixed field map. Now, what we want to know is which properties of a tower of fields or group is preserved under the Galois map, the appropriate map. Well, for this, all we need is the third part of the fundamental theorem of Galois theory. So this theorem tells us that a step in this tower of fields is normal if and only if the corresponding step here is normal. This is a major link between field theory concepts, normality, splitting fields, and group theory concepts, namely that this group is normal in this group. This is the big jump between field concepts and group concepts. Now, also, with regard to the fixed field map, if we have two subgroups of the Galois group, H contained in K, then because everything is closed in the Galois correspondence, H is the Galois group of its fixed field, so is K, and so H is normal in K. These are groups now, if and only if this is just rewriting these groups here. And now we can apply the fixed field map, and so the fixed field of the Galois group of the fixed field is the fixed field. Okay, and the order gets reversed. So the subgroups H and K, H is normal in K if and only if the fixed field of K is normal, or I should say it this way, if and only if this extension is normal, this field extension. So these Galois maps then are inverse bijections between normal towers of groups in field. They take normal towers to normal towers, and they are inverses of each other. Also, the third part of the fundamental theorem of Galois theory tells us that if this step is normal, and so we have normality on both sides, then the quotient group is isomorphic to the Galois group of the step. So this relates the Galois groups of E with various fixed portions to the Galois group of the step. So the Galois maps are also inverse bijections between any class of normal towers that has an additional property as long as that property is isomorphic invariant. In other words, if the property holds on one side of this, it also holds on the other side. And the critical examples for us are being abelian or cyclic. If either one of these is abelian, the other one is. And same for cyclic. Also, by the way, this tells us, or the second part of the fundamental theorem of Galois theory tells us that the index, which we're calling the degree to save a little windage, the degree of the group extension here is equal to the degree of the field extension. So the individual steps, the degree is preserved. So let Fe be a finite Galois extension. The Galois maps induce inverse step degree preserving. The degree of each step is preserved. Bijections between Galois tower decompositions or abelian tower decompositions or cyclic tower decompositions. All that matters is the isomorphic invariance here of the extension and the corresponding tower decompositions of the Galois group. Abelian goes to abelian, cyclic goes to cyclic, and conversely, both directions. An extension Fe, therefore, is tower abelian or tower cyclic, if and only if its Galois group is tower abelian or tower cyclic. I'm going to get a little weary having to say tower abelian or tower cyclic each time, so you can see it in writing, and I'm just going to say tower abelian. Now, there are, with regard to towers of groups, several important operations that can be applied to a tower of groups, and we want to determine whether or not they preserve relevant properties such as being abelian or cyclic. And in fact, we want to show they do preserve these properties. So let's take a look at, there are three of these operations. The first one is intersections. Let G be a group, and let A, B, and H be subgroups of G with A normal in B. Then it's easy to check that A intersect H is normal in B intersect H. And the second isomorphism theorem of group theory tells us that this quotient, which is equal to this, that's just simply because A is contained in B, this is where the isomorphism theorem comes in. This is isomorphic to this, which is a subgroup of B mod A. So, if AB is abelian or cyclic, well, I'm going to stop saying cyclic if I can remember to do that. If AB is abelian, that means that the quotient is abelian. Then so this quotient is abelian, therefore this quotient is abelian. Abelianness is inherited by the subgroup, which is then isomorphic invariant, so it's inherited over here. And so in short, if AB is abelian, A intersect H, B intersect H is abelian. And we can apply this to towers. If we have a decomposition of G, tower decomposition, so it starts with the identity, goes to G. If this is abelian, this tower decomposition, then for any subgroup H of G, this tower intersecting the first tower with H is also abelian. So if G is tower abelian, so is any subgroup of G. I don't know, maybe I should make a comment here. For those of you who have some familiarity with this, you will know tower abelian groups as solvable groups. And I did mention that once some time ago. But in this discussion, I felt it better to continue to use the term tower abelian, especially since the term solvable, its counterpart for cyclic is called polycyclic, but it's a very rarely used term. But this is more descriptive. It tells you that G has an abelian tower. Solvable doesn't say that immediately. So I prefer this term for now. At the end of our discussion, I'll, let's say, revert to the term solvable. Okay. Another operation we can perform on towers of groups is quotients. So we have a group G, A, B, and H are subgroups of G, and H is normal in G. Then if A is normal in B, then AH is normal in BH. And therefore AH mod H is normal in BH mod H. All this is, we covered all this in the group theory course. It may not be fresh to you right now, so you may, if you're concerned, stop and kind of review all that, or try to prove this yourself. The isomorphisms of group theory tell us that this quotient is isomorphic to this one if this cancellation of the h's, always a dangerous way to look at things, and that's equal to this, which is isomorphic to this, which is isomorphic to this rather ghastly looking quotient. But if AB is abelian, that means B mod A is an abelian group. The quotient is also abelian, and therefore this quotient is abelian. And so AB abelian implies AHH, BHH is abelian. And just as we did with intersections, we can raise that to the level of towers. We have a tower decomposition of a group G that's abelian. Then for any normal subgroup H of G, this tower is also abelian. And so if G is tower abelian and H is a normal subgroup of G, then G mod H is tower abelian. And the third operation is unquotients. So suppose G is a group, A, B, and H are subgroups. H is contained in both A and B, and H is normal in G. The correspondence theorem of group theory tells us that if AH is normal in BH, then A is normal in B. The third isomorphism theorem gives us this. And so we have AH, BH abelian implies AB abelian. And again, we raise that to the tower level. And so what we have is that here we have H normal in G1, subgroup of G. If G1 mod H, GH is tower abelian, so is HG. So when we raise this, the bottom group is H. Okay. Summarizing these three discussions, any subgroup of a tower abelian group is tower abelian. If G is a group and H is a normal subgroup of G, then G is tower abelian if and only if both H and G mod H are tower abelian. One more item that I haven't discussed, the symmetric group Sn is tower abelian if and only if n is less than or equal to 4. And as to the proof of that, well, in the group theory course, we showed that the alternating group AN is simple if and in other words, no non-trivial proper normal subgroups, if and only if n is different from 4. Also, the only non-trivial proper normal subgroups of Sn is An itself, the alternating subgroup. So Sn isn't solvable. Here I've used the term solvable. Shame on me, it should have been tower abelian. And I guess, no, here I said tower abelian. Not solvable or tower abelian for n bigger than or equal to 5 because the only candidates for an abelian tower for Sn are this one and this one, but neither of these are abelian towers. Okay, now, the property of being tower abelian or solvable, having an abelian tower decomposition, may seem quite special, and in a way it is, but it's also very common. There is a famous theorem called the Fate-Thompson theorem, and it says that any finite group of odd order is tower abelian. So that's a lot. The proof runs 255 pages, so I've decided to skip it. Let's look also at towers of fields. If we have an extension FE and an abelian tower decomposition, and we lift by any field extension, the result looks like this, and it is also tower abelian. So if FE is tower abelian, so is KE. Also, and this is important, well, I shouldn't say that, everything's important, I guess, but if FE is Galois, and this tower is also Galois, so what I'm saying is that the full extension is Galois and both steps are Galois, then FE is tower abelian if and only if the two steps are tower abelian. Full extension tower abelian if and only if the steps are tower abelian. This is the tower property, but it's in a very tight context. The two tower has to be Galois and the full extension. Everything has to be Galois for this to work. As to the proof of part 1, and this is something worth taking note of here carefully. Let's look at this tower again of fields. We lift the kth step by this extension. It's not appropriate to lift the kth step like you might think with the extension FK, because the way lifting is defined, the two base fields have to be the same. So we have FK minus 1 here, we better have it here. So what we're doing is lifting each step by a different extension. But it has the result of simply taking the composite of the tower elements with K. So we do this lifting. The corollary 531 tells us that the resulting extension, which looks like this, is abelian. And so the tower is abelian. So that takes care of part 1. Part 2, well, one direction is just concatenation. If both of these are tower abelian, both steps, then so is the full extension. You tack the abelian towers together. The other direction is a little trickier, but we can take a group theory viewpoint. We already know that if an extension's tower abelian, if and only if its Galois group is. So we can prove, this is the direction we want to go, that the Galois group tower abelian implies these two Galois groups are tower abelian. Well, the lower step, FK, is normal by assumption. It's Galois by assumption. So the third part of the fundamental theorem of Galois theory gives us this. We saw this a few minutes ago. And then theorem 7.10 tells us that both of these groups are tower abelian. And I'll let you sort that out. It's an argument I gave a few minutes ago. Now, for a finite extension, it might seem like being tower cyclic is more special than being tower abelian, but it's not. Tower cyclic extensions are tower abelian, but also tower abelian extensions are tower cyclic, finite extensions. And the way to arrive at that is the following. Say we have a tower of either groups or fields. Any tower formed by including or inserting zero or more additional intermediate elements, either groups or fields, is called a refinement of the original tower. So let's take a look at the group case first. Let G be a non-trivial finite group. Any abelian tower can be refined to a cyclic tower, in fact, whose steps have prime degree or index. As to proof, well, we don't have to worry about trivial steps. It's the proper steps that we're concerned with. Trivial steps are already cyclic. So suppose we have a step here, non-trivial step. The correspondence theorem of group theory says that the map pi that sends the intermediate subgroups, the subgroups of gk plus 1 containing gk, to the subgroups of the quotient, so it maps H to H mod gk. This is normality preserving and index preserving, and it's an order isomorphism. All that comes from the group theory course. Moreover, Cauchy's theorem tells us that if a prime p sub k divides this order of this quotient, then the factor group, quotient group, has a subgroup of order pk. It has an element of order pk that generates a subgroup of order pk, which by the correspondence theorem has this form hk mod gk for an intermediate subgroup. So we want to tuck this subgroup hk into the tower decomposition of G. But in order to do that and preserve the abelianness of the tower, we have to show that gk is normal in hk is normal in gk plus 1, and that the quotients are abelian. Well, the lower step is normal because this extension is normal. As to the upper step, since this quotient is abelian, this quotient is normal. All subgroups are normal for an abelian group. Then the correspondence theorem gives the normality of the upper step here. As to the quotient groups, this quotient is abelian because it's a subgroup of this abelian group. The third isomorphism theorem tells us that this quotient is abelian. So we can refine the original group decomposition, the tower decomposition of G, by inserting hk. And this quotient has prime order, so that that step from gk to hk has prime degree. Well, since G is a finite group, we can continue to do this, and it has to stop at a point where the non-trivial quotient groups have prime order. In other words, the non-trivial steps have prime degree, and everything is cyclic. We can now look at the counterpart of Theorem 714 for tower abelian field extensions. So if Fe is a finite Galois extension, then any abelian tower can be refined to, let's call it a prime cyclic tower. In other words, a cyclic tower in which each non-trivial step has prime degree. So this is really a direct consequence of our earlier corollary. We take the tower of fields, the abelian tower, and we apply the Galois group map, we get this tower, which is also abelian, but we've already seen this has a prime cyclic refinement, which looks like this. So these Galois groups are represented among the H's. And then apply the fixed field map. It'll take us back to a tower of fields that is a refinement of this tower. Because all the elements here of the Galois group are closed. So we apply the Galois group map, then followed by the fixed field map, takes us back where we started. So we get a cyclic refinement of this original tower of fields, and the degrees are preserved. So piecing together what we've done so far, we can say that the following are equivalent for a finite Galois extension. Fe. Fe is tower abelian, tower cyclic with prime degree steps. Galois group of the extension is tower abelian. Galois group is tower cyclic with prime degree steps.